Welcome to The Explainer. Today we're taking a look at a massive shift happening right now in artificial intelligence. We're talking about how code is transforming from being just a simple output into the actual infrastructure of AI. It's no longer just about an AI writing a quick script for us. Instead, we're looking at AI literally living, breathing, and operating within an environment made entirely of code. It's a total game changer.
So to really get this, we've got to fundamentally shift our mental model. You know how we usually think of large language models, right? As these sort of stateless brains. You ask a question, it spits out an answer, and boom, it instantly forgets you even exist. But here's the thing. For an AI to do real, complex, autonomous work over long stretches of time, those engines need a chassis. They need a structural layer that holds them, guides them, and lets them interact with the real world reliably.
Here's our roadmap for the explainer today. First, we'll look at moving beyond just writing code. 2. The code harness interface. 3. Mechanisms for the long haul. 4. Scaling up multi-agent teams. 5. Real-world agent applications. And finally 6. The next big open problems. Let's get right into it.
Section 1. Beyond just writing code, the paradigm shift. Okay, so historically we've always viewed code purely as an output, right? Just a transient, one-off generation. You ask for a Python script, you get your script, and that's it. Interaction over. But this new paradigm, it flips that entirely on its head. Code is now what we call the agent harness. It's an executable, stateful environment. We're completely moving away from an AI just spitting out lines of text to an AI continuously operating inside an inspectable framework, a place where its progress is actually saved, tested, and used to logically figure out exactly what to do next.
Think of a raw LLM like a massively powerful engine just revving on a test block. It has immense horsepower, sure, but it's not going anywhere on its own. That's where the agent harness comes in. It's the chassis, the steering wheel, the transmission. It provides the APIs, the sandboxes, and the memory needed to translate all that raw compute into steerable, long-term work. It's that crucial software layer surrounding the model that turns it from a forgetful conversationalist into a fully functional agent, one that doesn't just hallucinate or break down halfway through a job.
Moving on to Section 2, the code harness interface, building the machine.
So how does this actually work? Well, there are 3 fundamental ways code acts as this interface. Step 1 is code for reasoning. Instead of the model just, thinking internally in natural language, it externalizes its logic into verifiable code. Step 2 is code for acting. This is where the AI translates its high-level goals into actual executable commands. And step 3 is code for environment. This models world states and lets the agent actually feel the feedback of what it just did. Picture an AI tasked with web scraping. It uses reasoning to write out its logic, acting to literally command the browser to click and scroll, and the environment code to read the HTML response to see, actually, did that click even work?
And this harness interface, it definitely doesn't exist in a vacuum. It feeds into a massive, interconnected ecosystem. It starts right from the core mechanisms powering the AI, effectively turning intent into action. From there, it scales all the way up to shared infrastructures that let multiple agents coordinate. And finally, it branches out into these immense, real-world end-user applications. It's a highly structured framework, and it integrates literally every single layer of autonomous computing.
Which brings us to Section 3, mechanisms for the long haul, planning and memory.
Once an agent is plugged in, it absolutely needs mechanisms to stay on track. Because, let's face it, real-world tasks don't get solved in one simple shot. So agents use 4 explicit contracts for planning. First, there's linear decomposition. That's your basic step-by-step A to B path. But when tasks get messy, like diving into a massive existing code base, they use structure-grounded planning. This relies on things like dependency graphs to map out what to do next. Now, if the right path is totally unknown, they shift to search-based planning, which lets the agent systematically explore and simulate a bunch of different trajectories before committing to one. And finally, orchestration. This acts like the system manager, handling massive workflows by delegating the coding, testing, and repairing across totally different modules.
What's fascinating here is how this evolution in planning transforms a basic prompt from just a static request into a vital control layer. As the tasks get exponentially harder, the harness dynamically shifts from those simple linear paths into complex orchestration. And this is key. It keeps the agent's behavior bounded. It ensures that when the AI inevitably hits a roadblock or a bug, which it will, its plan is fully revisable. So instead of spiraling off track and breaking the whole workflow, it just recalculates and keeps going.
But here's the catch. Planning requires memory. And because LLMs have limited context windows and are notoriously forgetful, they rely heavily on something called context compaction. Think of context compaction exactly like your computer managing its RAM and a hard drive. It's an experiential memory system. It's constantly deciding, okay, what crucial info needs to be in my active short-term memory right this second, and what can I summarize, compress, and safely offload to my long-term storage. This mechanism is absolutely vital because it ensures an AI actually remembers not to make the exact same coding mistake twice.
All right, Section 4. Scaling up multi-agent teams, the ecosystem. So we've built the single machine, but what happens when you need an entire factory floor? Well, by operating over a shared code infrastructure, multiple agents can actually take on highly specialized human-like roles. Picture this. You've got a manager routing the tasks, a planner designing the architecture, a coder writing the script, a reviewer checking the logic, and a tester executing the code. And because they share the exact same code infrastructure, the reviewer agent can instantly execute and test the code written by the coder agent, flagging any errors in a shared log before the manager decides the next move. It is, quite literally, a self-correcting digital assembly line.
That leads us into Section 5, Real-World Agent Applications, the road ahead.
Now, I want to be clear, this isn't just theoretical anymore. Right now, as we speak, coding assistants are autonomously navigating live repositories to squash bugs. GUI and OS agents are literally driving computer interfaces as if they had their own physical mouse and keyboard. We're seeing automated lab scientists dynamically composing hypothesis testing pipelines. We have embodied agents powering robotics, reacting to complex physical environments in real time. And personalization models. They're creating adaptive user profiles that actively evolve over the long term. This whole framework is translating into massive, tangible benefits, turning AI into tireless operators across pretty much every industry you can think of.
And the pace of this research is just absolutely staggering. In just a few short years, we've rapidly progressed from simple text-based reasoning to fully immersive, executable world models where agents build lifelong skill libraries. This progression isn't just incredibly fast, it's fundamentally rewriting the core definition of how artificial intelligence operates on a day-to-day basis. Finally, Section 6, the next big open problems.
Because despite all this incredible progress, the machine is definitely not flawless yet. We still have some major hurdles. For one, we desperately need semantic verification. It's not enough that code compiles without crashing. We have to mathematically prove it actually solves the conceptual problem it was given in the first place. We also need self-evolving harnesses that can iteratively upgrade themselves without accidentally corrupting their own base logic. And as these multi-agent teams keep growing, managing their transactional shared program state without causing catastrophic code collisions? Yeah, that's a massive bottleneck. Plus, we critically need safe human-in-the-loop oversight to maintain strict boundaries and, frankly, accountability.
To wrap up this explainer, I want to leave you with a final thought to ponder. As we step into this autonomous future, and these AI harnesses become capable of optimizing and rewriting their own rules of engagement, where exactly do we fit in? Will humans just be a final checkpoint, or are we evolving into something else entirely? It's a fascinating paradigm shift. Thanks so much for diving into this with me today, and keep exploring.